The need for isotopic separation of water molecules containing protium, ordinary hydrogen, deuterium and tritium arises in various industries: production of heavy, D2O, water for the nuclear industry, purification of radioactive water from tritium during the liquidation of the consequences of the accident at the Fukushima nuclear power plant, and heavy water at nuclear reactors, reduction of the natural concentration of heavy hydrogen isotopes in water for biological and medical purposes, etc. There are many ways to separate water into hydrogen isotopes: isotope exchange in the presence of palladium and platinum, electrolysis of water in combination with catalytic isotope exchange between water and hydrogen, rectification, and other method. The existing technologies for the separation of hydrogen isotopes have a common feature: all of them, as can be seen from the table, are extremely energy-consuming and require the use of expensive equipment. When choosing a separation technology, it is logical to consider, first of all, the methods and processes of isotopic separation, in which the behavior of ordinary, protium, deuterated and tritium water molecules have the maximum difference. The energy expended for the separation processes should be minimal. These requirements are well suited for the phase transition when water freezes in a vacuum. However, it should be clarified that deuterium and tritium are usually found in water in the form of HDO and HTO. In this case, the freezing point for D2O is plus 3.8 degrees, and for 2, respectively, plus 9 degrees, HDO and HTO freeze, respectively, at plus 1.9 degrees and at plus 4.5 degrees. It has been established that, for example, at temperatures ranging from 0 to plus 1.9 degrees Celsius, water molecules with deuterium and tritium, in contrast to light, protium, water, are in a metastable solid inactive state. Water temperature and saturated water vapor pressure are interconnected, and the difference in the isotopic composition of hydrogen atoms and water molecules leads to a noticeable change in the temperature dependence of saturated vapor pressure. The difference in the physical properties of water molecules with different hydrogen isotopes in terms of the freezing point of water and saturated vapor pressure can be used to separate them when the pressure drops below 700 pascals. This feature of physical properties underlies the fractional separation of light and heavy water by creating a deep rarefaction above the water surface at low temperature. Light water evaporates intensively and then condenses, and the molecules of heavy water, being in an inactive state and having a much lower partial pressure, remain mainly in the evaporation tank with the source water. The proposed technology provides for a large number of evaporation and condensation processes on the surface of wetted nozzles in a special mass transfer apparatus, and is similar to the rectification process in this respect. The difference between this process and rectification is that the contact of the packings with the liquid phase occurs not constantly, but periodically, which makes it possible to cool the packings up to the formation of an ice film on their surface. In this case, the efficiency of hydrogen isotope separation becomes even higher, as can be seen from the dependence shown in the graph. Let's demonstrate the processes of phase transitions of water in a vacuum video from YouTube. Let us first consider the boiling of water at room temperature in a vacuum. Note that boiling is observed only in the upper layer of water, since only there the vacuum corresponds to the saturation pressure at the temperature of the water and the glass.
I got water over here. We're gonna fill it up, the beaker, with water. Boom. Then we're gonna cover it with the vacuum chamber and then turn it on and see what happens. You can see a little bit of bubbles start going, and whoa, it start boiling. How cool is that? Looks like it's boiling a lot.
The next two videos show that in a deeper vacuum, water not only boils but also freezes.
We're going to demonstrate reduced pressure boiling by creating a vacuum in a glass vacuum jar and using an Edwards pump. By using and applying vacuum, we're making water change from liquid to vapor very quickly and very effectively. Water at room temperature is placed into a beaker before putting it into a glass vacuum dome. We now open the vacuum isolation valve. You can soon see the vacuum gauge showing around 20 millibars of pressure. This is significant because it's the vapor pressure of water, and therefore the point at which it will boil at room temperature. At atmospheric pressure, water boils when heated to 100 degrees Celsius. That's because it's the point when water vapor pressure is equal to atmospheric pressure, and water begins to change phase from liquid to vapor. In this demonstration, we don't add any heat, but instead reduce the pressure. When this pressure is equal to the water vapor pressure, the water boils or changes phase, but at a much lower temperature. In fact, the energy for boiling is coming from the water, and consequently its temperature reduces, and as the pressure becomes lower, the water will eventually freeze. You'll see that even when removed from the vacuum chamber, the water remains frozen. A simple process, but one that's widely used in the pharmaceuticals and food packaging industries.
The proposed technology is aimed at making the process of separating water molecules according to hydrogen isotope simple and affordable with minimal energy consumption. This possibility appears when using a special heat and mass transfer apparatus. Unlike distillation columns, this apparatus is located horizontally, and the nozzles are located in the annular layer, which rotates, periodically dipping into the liquid in the lower part of the body. Near the end of the apparatus, heat exchange tubes through which a room temperature coolant flows, steam is generated, which then passes through the nozzles. The partitions between the mating sections of the nozzles are designed so that the steam path has a zigzag shape. In the lower part of the body, water with a low deuterium content flows towards the steam flow. The steam generated by the heating tubes, colliding with the developed wetted surface of the nozzles, exchanges molecules of light and heavy water on it, enriching itself with light water. The film enriched with heavy water on the surface of the nozzles, periodically immersed in running water, enriches it with heavy water. Thus, the vapor is cleared of molecules with deuterium and, after condensation, light water is formed. In addition to the mass transfer apparatus in which steam is generated, the plant includes vacuum pumps, a heat exchanger, a coolant circulating circuit, a circulation pump, shut-off and control valves, capacitive equipment and an ejector. An ejector located at the inlet to the volume compensator of the coolant circulation circuit ensures the creation of a low pressure at the outlet of vacuum pumps of about 3 kilopascals, which create a vacuum in the mass exchanger from 400 to 700 pascals. The creation of the necessary conditions for isotope separation under vacuum is ensured by the use of 4-vane Elmo-Riechel vacuum pumps of the RVWB series, which provide a volumetric steam pumping of 8,800 cubic meters per hour or 48 kilograms per hour. Compressed from 600 pascals to 3,500 pascals, the steam enters the plate heat exchanger, where it is cooled by a coolant with a temperature of 23 degrees Celsius and condenses into water with a temperature of 26 degrees Celsius, while heating the coolant to 26.5 degrees Celsius. Due to the low pressure of the condensate, the heat exchanger must be raised relative to the mass transfer device in order to provide the necessary pressure drop across the float valve that regulates the water supply to the device. The deuterium-reduced condensate can either be fed into the mass exchanger through a float valve to improve separation efficiency, or collected in light water collection tanks. The steam generation and condensation cycle provides a water circuit with a temperature of 23 to 27 degrees Celsius at a coolant flow rate of 2 kilograms per second. For the circulation of the coolant in the circuit, a cantilever centrifugal pump is used, into which water is supplied from an open tank. The pump delivers a coolant with a temperature of 27 degrees Celsius to the tubes of the heat exchanger located in the lower part of the mass transfer apparatus under the water level. Due to the low water pressure in the apparatus, it boils intensively, forming steam, which then passes through the layers of nozzles. The water in the tubes is then cooled from 27 to 23 degrees. The cooled water is sent to a plate heat exchanger to condense the steam compressed in the vacuum pump. The regulation of steam generation in the apparatus is carried out by changing the flow rate of the coolant by means of bypassing the boiler tubes. Regulation of the coolant flow in the bypass section is carried out by shut-off and control valves with an electric drive. Cooled to 23 degrees, the coolant enters the plate heat exchanger and, condensing the steam, heats up to 26.5 degrees. Next, the heated coolant under a pressure of 0.3 megapascals is sent as a working fluid to the ejector, which ensures the creation of a vacuum of 2 to 6 kilopascals in tanks for collecting light water. The water-air mixture after the ejector enters an open tank from which water is pumped out by a circulation pump, and air is discharged into the environment. Thus, with the help of this circuit, a cycle of steam generation and its condensation is provided without the involvement of extraneous sources of thermal energy, which makes the separation technology energy efficient. The source water for isotope separation is fed into the lower central part of the apparatus under atmospheric pressure at a flow rate of 48 kg per hour. Draining heavy water from an apparatus with a pressure of less than 700 pascals presents a problem, since the pressure in the drain tank must be even lower. This is achieved by connecting the drain tank to the ejector and setting the drain tank at a lower level than the apparatus. As can be seen from the brief description, the presented technology for separating heavy water molecules containing deuterium and tritium is quite simple and energy efficient. It is especially effective if it is used to purify water from tritium, since the difference between the freezing point of ordinary water and a molecule containing at least one tritium atom is 4.5 degrees. This technology can also be successfully used to obtain water with a low content of deuterium for medical and biological purposes.